Hi, today we're going to briefly introduce our paper get submitted to the ICCV. Our paper name is ViLLa, which represents reasoning segmentation with large language model. To begin with, we're going to introduce about what reasoning segmentation is about. Reasoning segmentation requires generating a binary segmentation mask based on an implicit query text involving complex reasoning. As shown in the figure below, referring or reasoning segmentation requires textual input from user, and then the model can, based on the input query and output the corresponding mask, which is more intelligent compared to the traditional segmentation task, and which makes the whole task more meaningful and more close to our daily life. And that's why we propose methods of solving this scenario. Methods such as Lisa or Pixel LM have investigated application of LMs to generate object masks in a novel reasoning segmentation task that requires complex reasoning to interpret sophisticated instructions. These approaches introduce efficient large language models capable of producing multiple open-set targets while accommodating diverse reasoning complexities. However, despite their successes, these methods remain limited to image-level reasoning and do not extend fine-grained reasoning capabilities to the temporal dimension. And that's why we are going to introduce our work, which have done more explorations in video reasoning capabilities. There are previous video reasoning segmentation methods trying to solve this problem. However, these methods can't handle multiple objects and are really prone to error propagation. On the right, ViLLa employs a video understanding model to select a keyframe for Lisa to segment and subsequently utilizes an object tracker to maintain temporal consistency. However, the quality of segmentation is highly dependent on the accuracy of keyframe selection, which is susceptible to error accumulation through propagation as the number of input frames increases. On the other hand, ViLLa adopts a sparse dense sampling strategy to compress visual features and extend the single segmentation token to track an instance across frames, especially when the movement is rapid. However, this sampling strategy fails to adaptively select the key video segments, making it challenging to capture the essential information from the video. Because of these drawbacks of previous methods, we propose our ViLLa to solve the challenges that previous methods have faced. To this end, we propose our ViLLa, which is an effective and efficient LLM capable of segmenting and tracking multiple objects with rapid motion, objects in crowded scenes, and objects in long videos with occlusions. To tackle the aforementioned challenges, we propose our ViLLa has mainly three-part components, and we are going to introduce them in the following pages. The first one is key segment extractor, which selects the most relevant video segments, which reduces redundant visual tokens and effectively turns long videos into shorter segments. We utilize a prompt-driven segment localization, which employs a prompting strategy to extract start and end timestamps of key segments, enabling precise temporal localization of relevant video content. Also, we use robust temporal aggregation, which averages top K model responses to determine the most consistent key segments. And finally, we are going to output the selected key video segments into the context synthesizer. In the second component, the context synthesizer synthesizes frame context information from visual features to text embeddings to generate contextually enriched text and highly input responsive visual embeddings. We especially use visual-aware text embedding refinement, which injects frame-specific visual features into the initial text embeddings using cross-attention, and this creates a refined text embedding that represents the current frame by synthesizing relevant visual cues. And the selection is based on the highest response scores from the cross-attention matrix. In essence, the contribution of this part is a mechanism to generate frame-specific, visually grounded text embeddings that are efficiently condensed to preserve only the most salient visual information relevant to the text query, contrasting with prior approaches using fixed sets of embeddings. And also, the core innovation lies in the attention score-based selection step. And in the third step, we use a hierarchical temporal synchronizer, which communicates and consolidates multi-scale segmentation embeddings across temporal dimension. In this part, the special segmentation tokens as well as the visual features are fed into the synchronizer and finally output the segmentation masks. And to be more brief, in this part, we managed to use the transformer decoder to separately refine frame-specific and video contextual segmentation tokens, and synchronize them layer by layer via novel momentum-based aggregation. So in this way, we can produce temporally coherent mask tracklists by ensuring the final video level embeddings incorporate precise and frame-aligned cues relevant to the overall video context. And the above pages are mainly about the contributions in our method design. And next, we're going to introduce a special contribution of our benchmark. For a more comprehensive evaluation of VRS, we established ViLLa-ICCV2025, a dataset containing text instructions, corresponding high-quality masks, as well as multiple choices. And to ensure reliable assessment, we collect a diverse set of videos from YouTubeVS, OVS, LVVS, MovieChat, and Video MME. Videos are categorized based on their duration, and to fully evaluate the reasoning capabilities, we designed two types of evaluation standards: multiple choices QAs and instructions and answers. We believe this new benchmark can fill in the gaps a bit of more challenging video scenarios in video reasoning segmentation. As for the result comparisons, testing on our newly proposed video reasoning stack benchmark, our ViLLa outperforms previous methods significantly. And on the traditional referring video object segmentation method, our method also outperforms previous traditional video object segmentation methods as well as newly reasoning segmentation methods. Finally, we are going to introduce you with the qualitative comparison. We show that ViLLa is capable of segmenting instances, the sheep with a black head, in crowded scenes with heavy occlusion. On the other hand, ViSA fails to track the sheep properly after occlusion with another sheep. And these results demonstrate the capacity of our ViLLa to handle complicated videos, demonstrating better discrimination, temporal consistency, as well as better conversation quality. And that's all of our brief introduction. Thanks for your listening.